All right, folks, so for electrostatics lesson number 4, we're going to talk about something called Coulomb's law. We could have started the unit with this, but I chose to leave it for the middle since it's the only time where we do math in this unit. So Coulomb's law is describing what's called the electrostatic force. So the electrostatic force is essentially the force that's produced between two objects that have a charge. At least one of them needs to be positive or negative. The other one can be positive, negative, or neutral. And so the electrostatic force determines the push or pull that two charged objects feel based on how far apart they are and how much charge there is on each object. So things that, we talked about how like charges repel and opposite charges attract. That means that the electrostatic force can be attractive or repulsive. It can bring two objects together, it can pull them together, or it can push them apart. And you need to know what the charges are, whether they're positive or negative, whether the objects will repel or not. So the equation for Coulomb's law is here. It's one of the busiest looking equations in all of physics that we look at. It's a force, electrostatic force. It's in newtons because it is a force, so it's a very real force between any two charged objects. So it reads the Fe equals k q1 q2 over r squared. And so most of these are new variables to us, and perhaps all of them are. So q1 and q2 are the charges of objects 1 and 2. So that is in coulombs. And so that's a charge. So it can be like two electrons, electron and a proton. It can also be like a cat and a wall. It can be any sized object, and no matter how many electrons or protons this Q's are the net charge. So we talked about that earlier, like if it's 10 protons and 12 electrons, then the net charge is -2. And so that would you'd represent that in coulombs, the charge of object 1. So it doesn't matter how big the charges are, these are the variables for charge. Whether they're positive or negative, we don't think about that for this equation. We assume that we just use them as positive, and then we determine the direction based on whether they're both positive, both negative, or one of each. R is the distance between objects that is measured in meters. So if you think about the way you learn about an atom, there's the protons in the nucleus, and then there's the electrons kind of zipping around, and there's a distance between those two things. It's an R because in an atom it's mostly thought of as a radius, but R in physics means distance in any direction between two objects. K is known as the Coulomb constant, and so we haven't used any equations, I don't think, that have a constant in them except for when we use little g. So it's just this number that represents some property of the universe. This doesn't represent something as concrete as acceleration. It's basically just saying that this is a huge number, and all that means is that the electrostatic force is a relatively strong force. All the fundamental forces have a constant that's applied to them. The bigger the constant, in general, the more strong the force. And so electrostatic force is really strong. It's 9 billion. So those are the variables. Now, for our purposes, you've seen some things in the lab, and you know that when you bring things closer together, more things tend to happen. And so there's two general relationships in this equation. The first one is if you manage to increase the charge of an object, it can produce a larger electrostatic force. So if you have two ions that have a small charge, they will have some amount of force. If you increase the value of the charge, then the force will increase. Think of it as taking if you have two magnets and you put them near one another, there's a force. If you snap two magnets together and then two magnets together, you have four magnets, the force gets bigger because there's more magnets. They create a stronger magnetic field. More charges create a stronger electric field. And so the greater the charge, the greater the force. And that comes out of the fact that the Q's are in the numerator of this equation. Now as far as r is in the denominator. And so the force will be smaller for objects that are further apart. And so the greater the distance you put between particles, the smaller the force is. And so that kind of comes out in the fact that r is in the denominator. The bigger the value of r, the smaller the value of the fraction, and the smaller the force. And so the last thing we're going to do has to do with using actual numbers. So we'll look at what we call proportional changes. Changes in variables, or there's a number of different names for it, but basically getting specific with numbers in how things change. Now in class, in like the assignment, you'll be plugging in numbers to the equation and getting a value of newtons. But what's more powerful in physics is being able to make predictions based on how much change is happening. So we have questions like this. By how much will the force change if the charge of object 1 is doubled? So we have the Coulomb equation, K Q1 Q2 over R squared. And so, you know, if there's two charges that are separated by a distance, they cause a certain amount of force between them. This is saying if you double the charge of object 1, what happens? So doubling something means that you're multiplying it by 2. And so it's possible to do this without writing anything down for the following reason. Okay, so the charge of object 1 doubles. And the way the fraction works, if you like double what's in the numerator, you're going to double the value of the whole fraction. So this doubles the numerator, and the end result of that is doubling the fraction. Whatever the charges are and whatever the distance is doesn't actually matter, because all we're focused on is the change. So if you double one of the charges, you will get double the force. And you know, there's lots of different variations on that question, but basically, like, whatever you do to one of the charges, the same thing will happen to the force. Now, if you want to think like down the line, how could this, you know, how could I like think about this in more complex situations? If I double one of the forces, sorry, if I double one of the charges, the force doubles. If I double both of the charges, I'm putting two 2's in the numerator, that will quadruple the force. And so, you know, when you change both of them, they each have an effect on the force. Our last example of this has to do with the distance between charges. If I triple the distance between charges. And so, you know, the general trend we talked about is if you increase the distance, then the force is going to decrease also. So here's the deal with this. You have r squared in the bottom. And so the way that we work with this, when you triple something, you're multiplying it by 3. What ends up happening when you do this is you multiply r by 3, but r is squared. So you are putting 3 squared in the denominator. 3 squared is equal to 9. So what's really happening is, because you're essentially putting a 9 in the denominator, so you put a 3 in for r, that gets squared, you are putting that into the denominator. What actually is happening is you are making the denominator 9 times bigger. When you make the denominator 9 times bigger, you are making the force 9 times smaller. And so the making the distance triple will make the force 1/9 of what it was. So tripling the distance will divide the force by a factor of 9. And so we'll be practicing with that kind of problem and others for Coulomb's law. Thanks.